Our speaker here is going to be Steve Weiner, and Steve Weiner is of the RPI class of 1978. After graduation, he spent 40 years at Sikorsky, and at Sikorsky, he's taken on some of the most important jobs in the company. He's currently the chief engineer of the SB greater than 1 Defiant. Prior to that, he was the chief engineer of the X2, which he started in 2003, and it set a speed record of 250 knots in 2010, and it also resulted in them winning the 2010 Collier Trophy. He was the director of engineering sciences from 2005 to 2013, and Steve won the Vertical Flight Society's Clement Award in 2012. Became an honorary fellow of the Vertical Flight Society in 2016, and he holds a number of patents on Fantail technology and X2 technology. So with that, I'd like to welcome Steve Weiner.
So let's start. So, like I said, a lot of this you have heard already, but this is really a unique and exciting time in VTOL history. New forms of propulsion, flight controls, distributed electric propulsion, useful autonomy. You see the picture there of the Sarah aircraft, which has matrix technology that Sikorsky has been flying around. Very unique missions. Okay, these very short duration missions that require high acceleration rates in order to get the kind of speed and throughput that the companies are looking for. Very different than what we normally do. Unconventional and very large funding sources, which may be the primary driver of everything that's going on right now. There's also been an openness to new development models. In the past, most helicopters were driven primarily by military requirements. That also includes the civil ones. But those requirements were very much prescribed, a lot of testing, a lot of reviews, 10, 15, 20-year development cycles if you got there, and some of them didn't. More recent times, we've been doing a lot of very quick development programs of manned vehicles. So I'm sure everybody can put together a quadcopter in a couple of hours and fly it around, and it's fine. But to build something that can actually carry people safely through a large-scale mission is a very different thing. And the safety aspect that Dr. Rosen brought up before, I'm going to get into in detail in a couple of charts. Also, there's an awareness for new certification models, and that was something Mark alluded to before. If we continue to test and certify the way we have before, the time period that we need to develop these aircraft are not going to change, and it's also not going to be open to the new technologies. Some of these you will test very differently than what we have in the past. Okay? Other components won't even need to be tested because of the levels of redundancy. So just kind of keep that in mind. So this is the good side. Oops, I lost the chart here. There we go. So the not so exciting piece, but very relevant, and number one is safety. Okay, and I can't really emphasize that enough. If you're building a vehicle to transport your French fries across town, it's a very different answer than if you're trying to send your child to soccer practice or something like that. Safety is number one. Always has been, always will be, especially with flying vehicles. Quite frankly, I don't care what the reliability of an automobile is. And when an automobile fails, you can open the door, get out, walk away, pick up call somebody to come pick you up or whatever. If you have a failure in the air, you wind up with fatalities, right? Not good. Part of that's reliability and availability and understanding what sort of levels you need to make sure that you have a viable system that works all the time. So the throughput that we've been talking about this afternoon, part of that means that every aircraft has to be available as you need it, or at least a very large percentage of the time. Very big driver of design choices. I don't care if you have electric propulsion, if you have 1 blade, 2 blades, 37 blades, really doesn't matter. You design differently depending on the level of availability and reliability that you need to reach. Then there's physics. So the bar chart on there is kind of interesting because One thing I have found remarkable over this electric propulsion revolution, and it is a revolution, is you see nothing about battery life with respect to ambient conditions. If you want to fly up here in Albany in the winter, it's very different than flying in Southern California. Your battery is not going to last as long. The cycle time will be very different. The number of cycles it lasts will be very different. You don't see that talked about, right? You can build a flying UAV, flying drone, right? And it flies very nicely, but nobody tells you what the performance is if it's 20 degrees outside, okay? What is your battery life? What is your time on station availability? And it changes. Public acceptance, we've talked about a lot, right? And I'm going to go into it in a couple of different aspects in a bit. And the last one is testing and certification. So for the students here, the first one that can name that aircraft gets to shake my hand later. Okay, that's the Lear fan. The reason you don't know about it is because it was never certified. It was the first all-composite aircraft of its type. The FAA did not know what to do about it. They made it test in 100 different ways, all kinds of different reviews and everything, and ultimately it was not certified. And basically the company, that part of the company basically went bankrupt. Okay, so something to think about. If you get something brand new, which is exactly what we're talking about, and your certification acceptance group does not understand what it is or how it works, you're going to be asked to test a lot more times, a lot differently, and you may not get out the other end. Okay, so let's talk about, from a designer's point of view, development models. So as a designer, the first thing I look for is what's the mission, right? Sometimes the customer does a really good job of defining them. They define the requirements, but historically, most recently on the military side, they will ask for hundreds of requirements, okay? So your design space as you start out may or may not be anything that you can actually wrap your hands around. Then the OEM, whoever it is, will try and shape those requirements once they kind of figure out where they might want to be headed. Takes a lot of time, a lot of effort, really not useful time because you're not improving the concept itself. You're trying to get the requirements to fit the concepts that you're capable of building. Okay, and that's not what we're talking about today. Then the customer will down select the concept if there's a competition. They may supply the primary propulsion or not. It all depends on the particular program. Then you got many multiple reviews and testing milestones. And the government will be the airworthiness authority. So ultimately, they can tell you whether or not they're going to accept your aircraft or not. What that normally results in is very long development times, program overruns, and occasionally cancellations. That's the Bell ARH there, probably the most recent example of a cancellation. And I would say it kind of fits probably 3/4 of those items that I have listed there. The other model is, and Mark talked to this before, build it and they will come. Okay, so Sikorsky and then Sikorsky and Boeing have done this 3 times in the past decade or so. Once first with the X2, then with the Raider, and now currently with the Defiant. But in that case, there's a very small number of key performance parameters that are defined. And I like to tell my teams that if you can't count them off on one hand, we have too many. All right, so 5 or less. The OEM will choose the propulsion system, right? Has nothing to do with the customer, right? Unless the customer happens to be an engine manufacturer. Then they'll choose a concept, right? And if the OEM is smart, they will be looking at multiple concepts. So the different pictures that Mark showed you before, really great, right? You look at all these different things, you see how it affects the mission, whether or not you can get an aircraft with value for the person you're trying to sell it to. Because it's all about value at the end of the day. The development testing in these cases were done by the OEM. Okay, we didn't go out and ask the government what we should test. Okay, we picked the pieces that we knew we needed to test. Sometimes we tested them more than the government would have normally asked for, sometimes a lot less, right? But it was done with thought. And then the airworthiness process, and this has been changing with the government, right? So they have now started looking at OEM airworthiness approval models, right? In our case, at Sikorsky, it's something called the Model Development Safety Committee. But they've been following along because they're trying to prevent what happened on the previous page, right? So a lot of open talking now, thinking about how you do this better. And the last one is probably the most important because, you know, your OEM and or the suppliers are the ones that fund this thing. So it's your own pocket that, you know, is going to be empty if you don't do it the right way. So very short development times. X2 flew in 3 years from the time we decided to go fly it. Low program costs. Again, X2, $50 million, flying development aircraft, and then usually high customer interest, okay, especially if it works. So the first one was really to demonstrate the physics. Rotor has been to demonstrate a operationally capable aircraft. So that's kind of the next step. Right now, with eVTOL and the things we've been talking about all day, we're pretty much in the prove the physics piece, slightly toward the operational aspects. Prove the physics, just get it off the ground, okay, that works. But to make it useful, you have to be able to handle different ambient conditions, different gusts, being able to say your crashworthiness is acceptable, have acoustic levels that the public will accept, that sort of thing. So that next step is the hard part, okay? Anybody can build a scale model with a particular concept physics-wise, and it may fly. When you scale it up, it's usually not that easy. And the problems you see may or may not be the ones you expect. Okay, so what do I do if somebody tells me we got to go design something new? The first thing I do is talk to the customer, right? And probably the biggest piece about that is, do they really know what they want? Sometimes they do, sometimes they don't. Sometimes you have to tell them you might have a concept that's very capable, that does things that they never even considered before, which in a lot of the VTOL work here, that's kind of sort of where we are. But if you go like the next step of this, if somebody gives you a payload range curve and says, this is what I want, well, now you got to ask them, all right, so what ambient condition is that in? Is it at 20 below zero? Is it 40 degrees C? Do you want to carry this payload through the whole mission? You want to drop it off in the middle of the mission or not? You have to start asking more and more questions. If they do know what they want, and you come up with a concept that works, then you really have to see if it's technically feasible. Okay, I was actually at a meeting early in my career where a sensor package company came in. They wanted a vehicle that could stay at 20,000 feet for 6 hours with their sensor package. Okay, and they came to a helicopter company. Said, you know, you're in the wrong place, guys. We can't do that. All right, and you have to be able to understand what your concepts can and can't do to be able to answer that question. The next one's probably the most important, and this is the one where I say you better be able to look yourself in the mirror after you answer the question. Have you done trade studies, or are you already tied to a concept and you're trying to mold everything to fit into your concept? It's a very, very hard question, right? Because sometimes your company may only have one or two concepts that they're playing with, and they may not be willing to go into another direction. But at the end of the day, you better have a concept that not only do you believe in, but that works and that you can build. So I was glad to see the auto production line stuff there, but you know, can you build it? Do you need digital printers the size of a house in order to build your vehicle at the rate you're looking for? If that's the case, what's your manufacturing plan? What is your MRL? Where are you investing the money to be able to go build that stuff? Talked a little bit before about how you certify, right? If it's something really different, you need to be thinking about how you're going to talk to the Airworthiness Authority about how you're going to certify your vehicle, okay? And then the last part is, are you fully funded? Do you really have a robust business case? Because at the start of these new technologies, you're going to have failure after failure after failure until you can actually get things to work. And I don't care what concept you have, that's just what happens with new stuff. And you better be able to maintain your pace, otherwise you're not going to have anything coming out at the other end. So doing your homework like this early really will prevent the fatal program errors technically. All right, so I thought up until Ken talked a minute ago, I thought I had one chart that didn't touch on something anybody else had said today. That was it. We're good. So you took care of that one. So, okay, simple safety math for urban mobility. So here's the S-92, you know, a modern helicopter flying out there today. We have triplex voting, you know, for flight controls, fault-tolerant design, can take a lightning strike, HERF, DALE software. Don't kid you, I'm going to talk about that more in a little bit. 2,000 plus flight hours a year. Where flight critical components are 9.9, so a failure per billion flight hours. If you integrate that out, that's one loss per million flight hours. Now take the kind of numbers that we were talking about a minute ago, right? With 50,000 aircraft, 3,000 flight hours per vehicle per year, one loss per million flight hours. That's 150 accidents per year at the current best-in-class safety standards. Okay? So think about that. Think about public acceptance. So right now, if a news helicopter goes down safely, okay, it's all over the media, right? Think about if we had 150 accidents a year, okay, with this new design, okay? And I guess what I'm saying is, what we've done up to now, with the kind of numbers we're talking about, is not good enough. We really have to start thinking about how you do it better. So
Well, that's why I've said 10 to the minus 7. In other words, you need to get 1 per 10 million,
yes,
not 1 per million.
yes,
And that sets the requirement for the new craft. If we're going to if it's going to change society the way Mark is trying to do.
Exactly. So, is this the next one? Okay. All right, so how do you get safety, right? So first of all, you got to take a look at your concept. You have to do a real failure modes and effects analysis. You really have to dig into every one of your parts, even your reliable electric motors, even your other components that's never failed. You really have to look at it in detail and come up with what the potential failure hazards are. And they may not be the ones that historically have happened before. So you really have to sit there and think, if every worst condition happened, how would my vehicle react? And then you got to figure out how you got to test those critical components to make sure they last. The other part that we didn't really talk much about is emergency procedures. And I get the fact that we want to be able to land on the parking lot rooftops, but the bottom line is auto rotation is probably the biggest safety advantage that helicopters have. Low disc loading, being able to have a controlled landing, all right? And I understand that from a battery life point of view, having 30 seconds at the beginning and 30 seconds at the end for VTOL helps with the design, but it may mean that the design we're looking at is not the correct one, or we have to augment it. And whether we augment that with additional power sources, or we figure out how many rotor systems we can lose and still maintain a sink rate that's low enough that a landing gear can handle, okay, that's what we got to think about. If you have loss of control, what happens, right? So I was very happy to see a couple of the projects that the students were working on dealt with what happens if you lose one rotor, right? How do you do heave, once you lose one? Other things I think about are, as you're landing, right, what happens if you happen to lose a rotor? And you've got half of your rotors in ground effect and half out of ground effect. Do you have sufficient control bandwidth and functionality and speed to be able to handle that? Okay, not an easy question. The auto parachute we saw on one of the items that Mark showed, I think that's really the way to go. It's almost like the standard. The problem is, what do you do with think about this, a parachuting eVTOL in the middle of New York City? Where does it land? Right? So being able to get to a point where you can then land somewhere under control is kind of critical. Do you have a manual override if you have a fully autonomous aircraft? So making it simple enough that anybody that's not a pilot at least can be able to land it, I think is something that needs to be studied some more. And again, what's the landing footprint? So the next one is a pet peeve of mine, because we have an all-electric aircraft, all-electric flight controls, all-electric everything, and we have people that can hack into Teslas and make them crash into walls. Okay, how do you prevent this on this aircraft? I think it's got to be hardened like a military aircraft. Okay, I think you need multiple software models within your flight control system so that if you do have a failure, you can switch to the other one. Okay, what's your voting protocol if you have a failure in one of your flight control systems? If some kid decides that he's going to shine a green laser in your pilot's eye, or if you're autonomous, in your sensor, right, and that sensor is your pilotage sensor, okay, what do you do then? Okay, so like I said, you're almost thinking military hardening now, even for a commercial vehicle. Again, because of the safety question. And then if you happen to have to crash, then what do, right? Are you doing a 6 foot per second landing gear? Are you doing a 42 foot per second landing gear? Are you doing no landing gear and you're on an airbag? Do you have the parachute at the last minute? That sort of thing. Very big design choices. On a vehicle this small, packaging these systems is going to be a problem. Okay, so it's got to be thought about at the beginning. It can't be an add-on. Okay, and then the last part is any failure mode's unique to your concept. So we showed the Firefly up there before. Okay, one of the things we spent a lot of time on was overheating of the batteries. And on a crash, what's going to happen? Are they going to burn? Are they going to ignite some other fluid that was part of the aircraft systems itself? Okay, so you really have to look at what your systems are, all right? And say you decided to cool your batteries. If your cooling system fails, how long do you have before you got to land? Okay? All right, so again, safety not optional. One incident can end your business plan. Originally, I had a picture of the 61 on the top of the Pan Am building, and I decided to take it out because I figured the only person that's in the room that would be able to remember that were the class of 78 guys and Ken. So I said, by the way, I don't know if you guys know, but we have a third of the Aero class of 1978 in this room today. We only had 10 people in the class. We only had 10 people in the class, and 3 of us are here today. Okay, so once you decide you need to go to that point, and I absolutely agree with Mark, designing and testing for safety is complex and costly. So we got to pick the right ones to go test. Some of these may not impact, right? We get rid of a lot of the mechanical flight controls, swash plates, that kind of thing. You may not have to do the kind of testing in the upper left, but fault-tolerant testing certainly is something that should be on the table. Certainly HERF with the all electronic controls, lightning strike. If somebody takes a strike, I know we're talking VFR now, but ultimately this won't make sense unless you can do it IFR. So, something to think about as we move forward. All right, so a lot of these were talked about already today. How many nines? Sensor specific, right? So again, if you're autonomous, what sort of reliability do you need in the sensors to make sure that you can make it to the next landing zone? Redundancy management, so your distributed propulsion system, right? How many do you need so that if you have a reasonable number of failures, you can still continue flying? So the next one, for those of you not familiar with normal reliability acronyms, that's mean time between mission affecting failures. So in order to have the availability that we're looking for to be profitable, okay, you have to keep that number as low as, as high as possible, okay? And then modularized maintenance, we talked about, doing a quick charge of the battery right in between. If you're there for 5 minutes, if you have a battery that can be replaced in 5 minutes, maybe you don't have to do that. And maybe ultimately it's a better answer efficiency-wise for the aircraft. Because I'll tell you what I worry about the most of about these designs. They're very inefficient weight-wise. The weight-empty fraction is huge because your fuel is with you all the time, even if you can't use it anymore. Okay, batteries are heavy. Okay, a normal helicopter's performance increases as you burn off your fuel. These vehicles don't change. Okay, you're carrying that dead weight around all the time. So when we talk about only electric, I'm thinking maybe a hybrid might be an answer, or a very mild hybrid might be an answer. Okay. Okay, testing and certification, we already talked about this in general, but the bottom line is you better be able to test the parts or know somebody who can test them to the right levels of certification. And the second bullet there, do they consider you a rotorcraft, an airplane, something else? That very much changes what you're going to be testing. All right, so we're getting to the end here. So public acceptance goes along with operational feasibility. So when I look at these type of vehicles, and we're talking about many aircraft in the airspace at a time, I'm thinking that I need to be able to hover, or at least station keep, for X amount of time if the guy in front of me had a problem. Okay, what am I going to do if the first guy landed and broke a landing gear and they can't move him off the pad? Do I sit there for 5 minutes while they drag him off? Right? I have to have the power capability to do that. And whether that's a bigger battery or some emergency power capability, you need to be able to do that. So while the time on station versus range, we may not be talking about 8 hours on station, I do think it has to be more than measured in a minute or so. Okay? And if you think about how helicopters fly anyway, and VTOLs fly anyway, with these small mission segments, it's more about acceleration than speed. Okay, if you think about how long it's going to take to accelerate from a hover to any of the aircraft's top speeds and then decelerate again, if you can accelerate faster to a lower speed, keep the area under the curve the same, you may wind up with a better solution. Okay? So the part of that's listening to your customer. So no disrespect, Mark, but I was listening to the customer here a minute ago, and he said he wants wings. And I'm thinking, why? Okay? You can go fast without wings. You may even have a better answer without wings. I want that design space as big as possible. I don't want to narrow it down right now at this stage of the game. Okay? I may be able to come up with a lighter, cheaper, better value answer for him if that part of it's open. Okay, control system and lift system interaction. So we talked about that a bit. You see the picture of the V-22 with one rotor off the deck, one rotor on the deck. One's in ground effect, one's out of ground effect. Do you have sufficient control power to be able to handle that, especially in the case of a rotor failure on a multiple rotor machine? Okay, and while you're doing that, okay, can you then get back into flight or your landing state and be land safely or continue your mission? All weather operations we talked about, the cold weather performance, you really need to look at, because that's what's going to size your battery. Okay, whether it's the number of cycle end on the hot side or on the capacity end on the cold side, that's what's going to size it. And whatever reserve you decide to put into your machine. And again, that's dead weight. Okay? You really have to think of it as dead weight. Acoustics. All right, so I agree 100%. That is the primary rotorcraft acceptance issue. The question is, what are you trying to design it to? Are you not any louder than the electric car that's driving by, which doesn't make any sound? Because in the future, that's what it's going to be. You're right. It's not going to be big diesel trucks spewing black plumes out the top with bellowing sounds, right? That's what it's going to be. But you also have an acoustic issue inside. You're going to be carrying passengers who are going to be used to the environment that's in a car, all right, or a train, or that low level of acoustic, acoustic level. Do you need to do anything special to get down to that level? That adds weight too. Okay, so you got to think about that a little as well. And then the operational concerns. So we talked about, again, the effective disloading of your aircraft is going to determine what your auto rotation capability is going to be. But where you land, all right, so you have a picture of New York right there. If you can't land on that rooftop you're aiming for, all right, and you have a failure, where do you land? Okay? And that part of that comes back to the autorotative index, which is a historic measure on regular helicopters. There's going to have to be another one come up that we come up with for these type of distributed propulsion aircraft to be able to get some measure of goodness as to your design. And then the infrastructure piece, I think Mark talked to quite a bit. So, in summary, I think this new design space really provides unique opportunities. I agree. This is the 1950s when turbojets came in place and people would design an aircraft with every kind of swept wing, straight wing, engines on the tail, engines under the nose. Fantastic time for a designer. I think achieving the acceptable safety levels are going to impact the design more than you think. And it's going to be the primary impact on the design for the number of aircraft we're talking about in the flight space that we're talking about going forward. I think operational closure of the design may force a hybrid design. And that's just me looking at it from 10,000 feet. Once we get into that kind of thing, then you can figure out exactly what you need. Public acceptance, still the key driver. I can pull out magazines from Popular Mechanics from the 60s, helicopter in every garage, blah, blah, blah. Again, no landing spaces, public perception of safety, noise, same things we're talking about today, okay? Still the same things. And I'll tell you, the question that was probably the most to the point today was Bill Lewis's question to Mike Hirschberg with regard to what are we doing as far as getting that infrastructure, working with the cities, working with the places you want to operate in to make that part of their design. Okay, that's the hardest thing that we have to face here. And then testing and certification has to be considered from the start. So that's what I have today. So any questions, I'd be very happy to answer.
Steve, thank you. Very good talk. You strike me as a highly experienced designer. And I guess I had two questions, actually. One is, if I handed you a napkin and I asked you to draw what the concept would look like based on what Mark needs, what would it look like?
I honestly don't know right now. And I'll tell you, the part that the safety issue is the thing that I'd have to look at first. I don't necessarily think that, I think the complication of tilting rotors, moving rotors, stowing rotors is going to place you in a reliability and availability position that may not allow you to close your design. I'm a simple is better guy, all the time. I think a lot of it really has to do with the real performance of a battery electric system, all right, and what the real weight empty fraction is. And honestly, I haven't done enough work on that specific propulsion concept to really tell you. But what I will tell you is it will be low disk loading. It will most likely be, well, I think it has to be constant speed because of the acoustic question. And I wonder why more of these don't have collective. Not cyclic, but collective, so you can keep tip speeds constant. Because I think unless you do that, you're never going to get a real answer. It will also open up a huge design envelope for the control end of it, okay, that we're not considering right now. So I think complication in that particular aspect, pretty easy to deal with if you're just talking about collective, right? You do it with an electric motor, no big deal, right? I think that's the one feature I think that would be on whatever we design, okay? And I really think that unless the battery technology has advanced a little bit more, you're almost going to be forced to a bigger battery than you need or a hybrid.
I have a second question, but I don't want to take up everyone's time. So, but mostly, when will this happen in your mind? When will I be able to hit the app and get on Uber or get on an aircraft and?
So technically, you can do it now. Okay, you can sit down if you spend, if I could take 30 people here and put them in a room and we can figure out what it is in probably 2 or 3 months. The problem is the execution. Okay, and the execution. Honestly, it's more infrastructure and public acceptance than anything else from where I sit. Okay, it's never been a technical issue making something fly and go the X distance here and there. The great news is, I looked at Mark's spec, right? It doesn't have 5 KPPs, but only has about a dozen, right? It's really, really well put together. You can build an aircraft to it. All right, but being able to actually produce it in quantities and have the public accept it from a safety and a noise point of view is really the issue.
I have to comment on it because I know you're more positive than you're coming across. In other words, there is a revolution coming and you guys have to lead it. The only thing that Steve's pointing out, I believe, is some of the challenges that he sees. Don't get turned off on this. You can do it, and it's your turn to do it.
Didn't I say we could do it now?
Well, no. But the one, if I would be permitted to give you a comment, the one area I would start with and decompose is this 1 in 10 million flight hours. And then I would decompose the reliability numbers to all the subsystems. Now notice what Steve talked about. He went down to the subsystems because that's where the problem is going to be. It's going to be in some weirdo bearing or some nut that isn't tightened right or gosh knows what else. The point is, it's that kind of thing that becomes the oh by the ways that gets you. It's real easy to say, hey, it's just look, we want to optimize hover power loading. We want to optimize L over D. Give me a mission. I can crank out an airplane. And I can, parametrically play games with my propulsion weight empty and my overall weight empty fraction. We all can do that. Everybody in the room can do that. The issue is, can you come up with something that's affordable, extraordinarily safe, and have absolute confidence on the part of the public? That's the challenge. It isn't, playing the L over D game alone.
I agree with what he said.
Should he drop the mic or?
Unless somebody else has a question. Uh-oh, my roommate.
So looking back now, what advice would you have to these students of the class of 2018 or 2019 or 2020?
I think you're at a very unique point in the development of VSTOL. And you're not going to see this again for a long time, right? That Wheel of Fortune, right? I use that all the time. For some reason, I didn't use it this time. I was glad. But everything on there had an advocate, right? You had somebody who's, oh, look at this, it works just fine. And because of all of these other peripheral features, capabilities that weren't there, they failed. A lot of the pictures of these new vehicles that you've seen today they're not going to pass the test as time goes on. And eventually there's going to be one or two concepts that are going to make more sense than the others, right? It's up to you to find that. And again, you got to look at it with an open mind, all right? And the other thing I would give you advice is do what I did when my advisor at RPI, when he found that I was going to work for Sikorsky, he told me that I was throwing my career away. Don't listen to those guys.
Hypersonics.
No, he just hated helicopters, so. Okay.